All right, this is lesson 3.7, finding dy over dx and d squared y over dx squared. So we're finding the first and second derivative, and we're going to use implicit differentiation. Here's the original equation. So we'll start by just differentiating each piece. So the derivative of y squared, we multiply by 2 out front. We take that exponent down to a first power, and then by the chain rule, we copy down the y. Then we have to multiply by the derivative of y, which is dy over dx. Now I'm going to erase that 1 because that's y to the first, but it looks like y prime, but it's really just y. Equals derivative of x squared would be 2x, the first power. You could put times the derivative of x, which would be dx over dx, which would be 1 times by 1, but I'm going to leave that off. Plus the derivative of 2x, which would just be 2. Then we'll just simply divide by 2y on both sides. Leaves us with this, dy over dx equals 2x plus 2 over 2y. Or we could simplify that by dividing each term up here by 2, which would give us dy over dx equals x plus 1 divided by y. There's our first derivative. That would give us the slope of the curve of the tangent line, or the slope of the curve at any xy coordinate. To find the second derivative, we're going to do the derivative of this. So the derivative of the left side would look something like that. The derivative of the right side, symbols would look like that. So the d over dx means I'm doing the derivative of the derivative. So this left side then becomes d squared of y, or the second derivative of y, with respect to x squared. On the right side, to get the derivative of this, we're going to use the quotient rule. So I'm going to use low d high minus high d low over low squared. So low d high, so low would be y. D high, the derivative of x plus 1 would be 1, minus high, which is x plus 1. D low, derivative of y would be dy over dx. And that would all be low squared, over low squared. One important thing to remember is when you do high d low, put that high in parentheses, because x plus 1, we need to take the x times dy over dx and the 1 times dy over dx. So, continuing down here, let's copy down the left side again. 1 times y would be y, minus x plus 1. At this point, we're trying to solve for second derivative. I'm trying to come up with a second derivative expression. I want to, in place of dy dx, I'm going to substitute what I know equals dy dx, which was over here, x plus 1 over y. So substitute that in right there. It'll still be over y squared. At this point, we have our second derivative, but we really don't like to leave a fraction within a fraction, so we could go through and multiply each term by y. So I can multiply by y here, and by y here. As long as you do the same thing to all three terms. This is all one term because it's multiplied together. So I'll multiply here, here, and here. That will allow me to cancel off these y's. So then that would leave me with second derivative of y with respect to x equals y squared minus, now I'm going to FOIL this out, so x times x would be x squared, x times 1 would be 1x, 1 times x would be another 1x, that would be 2x, and then 1 times 1 would be 1, over y squared times y would be y to the third. Now most likely, most textbooks or most teachers or professors are going to ask you to simplify it a little bit further, because we know what y squared equals. Y squared is equal to x squared plus 2x by the original problem. So we can substitute in place of that y squared, what y squared was equal to, which was x squared plus 2x. So a lot of times when you're finding second derivatives, you will have to substitute in the first derivative expression someplace in the problem, and then a lot of times at the end you can substitute in your original equation back into the problem. that's gonna allow us to simplify this quite a bit, because x squared minus x squared would be 0, 2x minus 2x would be 0, then you distribute this minus, we're gonna have minus 1 over y cubed as our final answer. That is the second derivative of the original expression.